Pleasure to have Hao Jia from the University of Minnesota, and he'll be talking about linear vortex symmetrization as far as the spectral density function approach and Gevrey regularity are concerned. So go ahead, Hao.
Thank you, Andrea. Thank you for the introduction and the invitation. It's a great pleasure to give the talk on this occasion. Of course, we would like to meet in person, but hopefully that day will not be too far away. Okay, thank you very much for everyone to come here. So today I'm going to talk about some, firstly review some older results and then talk about this new work on the so-called spectral density function. So the first half of the talk is kind of about older work. So for the experts here, you probably have heard the talk multiple times, and I apologize for that. So this is based on joint work with Alex Ionescu. Oops. So we know that of course fluid flows are three-dimensional, but many flows that occur in oceans, atmosphere, and plasmas are approximately two-dimensional. And these flows are often dominated by a single vortex or a group of interacting vortices. And there have been a lot of interest, both from mathematicians and physicists, in understanding at least heuristically simpler two-dimensional flows. So here I have clipped two papers. The first one by Mike Williams, who had done a lot of work on the vortices and its role in the so-called two-dimensional turbulence. And on the right, you have an experiment, which is actually on electron plasmas, but surprisingly satisfy the same equation 2D Euler. So you have this. So here you have this elliptic vortex, but then you run the flow, and then what you observe is that it gets symmetrized. So this axisymmetrization in 2D flows is the main goal that we want to prove rigorously. So in an attempt to understand this phenomenon rigorously, we study the asymptotic stability problem for the two-dimensional Euler equation. So let's recall the 2D Euler equation. You have this in this vorticity formulation. So you have Pach T omega plus U dollar gradient omega is equal to 0, and U is given through the Beer-Savart law from the vorticity field. So you firstly solve Laplace equation to get the stream function, and then you take the perpendicular gradient. So it's well known that smooth solution to 2D Euler equation is globally exists globally and remains smooth for all times. So in terms of regularity, really the problem is well understood, but that's not the case for the long-term behavior due to the lack of global relaxation mechanism. So if we look at this equation, it seems that we cannot really reasonably expect any regular behavior, because you just have this nonlinear transport equation where the velocity is determined from the vorticity. So one might just expect some chaotic behavior. But actually, it turned out that that's not the case. So in numerical simulations of, at least for slightly viscous 2D flows, we often observe two striking processes. The first is the previously alluded axisymmetrization phenomenon for vortices, and the second is the so-called merging of same sign vortices. So the first one is what we are primarily concerned. The merging of same sign vortices are extremely interesting, but it's highly nonlinear, and even the physicists have some difficulty in figuring out why that's the case. So here we have this numerical simulation due to Theodore Drivers, but you can actually find it in many places, even on YouTube. So here you start with some almost like a random distribution of vorticity, and then you run 2D Euler. You see this. You see that the kind of the vorticity field gets cleaned up, right? You have this vortex symmetrization phenomena where the small perturbations of this vortex just gets absorbed as a part of the vorticity through this axisymmetrization process. And then if you have two vortices, highly concentrated vorticity region, if these get close together because of the larger scale fluid flow, then they could also merge together. So that's the merging of same sign vortices. But in the end, this actually the numerical simulation will run for quite a a long time. But in the end, what you would see would be just two vortices of different size. Okay, so that's what happens, at least for slightly viscous fluids. So
how?
Yeah.
Can I ask a question?
Sure.
So, so you say that this simulation is for slightly viscous fluids, right?
Well, you have to ask Theo, but he told me actually it's for 2D Euler, but the numeric scheme could incidentally introduce some small artificial viscosity.
I see. So basically the idea is that somehow when the viscosity is small enough, the video looks the same, independent more or less of the viscosity. So basically it works for Euler. Is that correct?
That's my understanding, right?
Okay, thanks.
So, yeah, thanks for the great question. So actually, for the Navier-Stokes in R2, there's a very beautiful, elegant result by Galli and Wing, who prove that actually the solution, the vorticity field, will converge to an O-syn vortex as t goes to infinity. So this actually works for all kind of data, for all viscosity. So then this gives us a really clean picture, right? As t goes to infinity, you will only see one O-syn vortex. So how do we understand these two different phenomena? Well, I think one could, in our context with small viscosity, one could understand Galli and Wing's result as the so-called ultimate dynamics, where all these interesting merging and the symmetrization process have been finished. Then you see only one O-syn vortex. But so here we are more kind of interested, if we consider small viscosity situation, then we are more interested in the intermediate dynamics before this merging and symmetrization process have been finished. And this is the process where we believe that the viscosity is not the dominant feature, because the viscosity in all this are very, very small. Okay, so in this talk, we consider the first process, which is symmetrization process. So that's to do that on mathematically rigorous level, we study the symptotic stability problem for 2D vortices or shear flows. So vortices are just radial solutions for the Euler equation. You have vorticity field, which is a radial function. So as long as vorticity field is radial, then it's automatically a steady state. So we can study its stability. Another situation we study is a shear flow. So shear flows are parallel flows where the velocity field is only along one direction and the velocity field depends only on the y variable. And it's here we study the domain where it's given by the periodic channels. So x is periodic and y is from 0 to 1. So this looks a little funny, right? X is periodic, but okay. So here I view this as kind of a model for the vortices, because in the vortices, if you consider polar coordinate, you have theta and r, right? Theta is automatically periodic with period 2 pi. So that's exactly correspond to x. So the stability problem is a very classical problem and has been studied by many people studying from the 19th and 20th century by these pioneers. And also more recently, we have a lot of progress on this classic topic in both linear and nonlinear stability. So before we go into the details, maybe it's worthwhile to discuss the several different concepts of stability. So so on the nonlinear level, we have this nonlinear orbital stability. This actually has been proved by a quite robust method by Arnold, and also some recent work by K. Choi and Galli Svirac for vortices. Actually, for the vortices, we are interested in nonlinear stability is actually known. So these are based on okay, not an issue, but maybe okay. So the main thing about the orbital stability, that the control is quite weak. Okay, you get some, because you are based on some fixed monotonicity quantities, so you get control in some sort of L2 space. Okay, if you ask the more detailed behavior, you cannot really get those behavior. And also there's no dynamical information. You don't know, for example, you cannot really see the rotation of the vortices. So and so we are more interested in the asymptotic stability. So that's kind of a more precise description of the dynamic. And also okay, if we study stability, then one important thing is to start is the linearized stability. So here we have two kind of things. Firstly is a so-called unstable discrete eigenvalues. So if you have discrete eigenvalues, then if the discrete eigenvalue correspond to unstable situation, then you have exponential instability, right? That's a quite bad behavior. So usually we do not consider this. And then there's the behavior corresponding to the continuous spectrum. Here it's more delicate. It depends on the situation. So for us, maybe the most important example is the following simple equation. If we look at partial t omega plus I by omega is equal to 0. So here I only consider omega as a function of y, not a function of x. Okay, so it's just an example. It's not the 2D Euler. So here, let me assume that y is from 0 to 1 and by is strictly monotone. Now this this equation, of course, can be explicitly solved, right? You have the solution omega ty, and this is given by omega naught y e2 minus I byt, right? This equation is explicitly solvable. Of course, if you study the spectrum of this operator, say from omega to by times omega, it has continuous spectrum from b0 to b1. Now, okay, so the solution, so the continuous spectrum gives the following behavior. So because we assume by is strictly monotone, you can see that, let's assume that also that omega naught y is smooth. Then you see that this function, because of the increasing oscillation as t goes to infinity, this function will weakly but not strongly converge to 0 if right. So for sufficiently smooth omega naught. So this is the kind of the behavior that we want to understand for 2D Euler. And also you see that because of it's only weakly convergent but not strongly convergent, because if you take derivative in y, the derivative will grow linearly over time. So it's a weak convergence behavior. So, we also see that if you remove this oscillatory factor, okay, you have this oscillatory factor. If you remove the oscillatory factor, you get a so-called profile, and then this profile stays uniformly bounded. So these two kind of features are important for the 2D Euler as well. So you have weak convergence, so you cannot control the vorticity for all times in a smooth norm, but on the other hand, if you correctly modify the vorticity, then you can possibly get a profile for which you can get the uniform control over time, smooth control over time. Okay, so let's firstly consider the shear flow case. So let's assume the shear flow is strictly monotone and spectrally stable. Then we try to understand the stability. So let's linearize around this flow. So this is the shear flow with small perturbation u, and with the corresponding vorticity field given by this. So then if you plug in this to the 2D Euler, assuming these are the solution to 2D Euler, you get this perturbed Euler equation. You have partial t omega plus by partial x omega minus b dot prime y partial x psi plus u dot gradient omega is equal to 0 in this domain. So t is positive, x is periodic, y is in a finite channel, and u is given through the Beer-Savart law. So you look at first glance, this looks more complicated than the 2D Euler, because you have, in addition to the 2D Euler, you partial t omega plus u dot omega, you have two more terms. But in reality, these two terms will give you a stabilizing mechanism, and the dynamics is actually simpler for small solutions, simpler than the 2D Euler equation. So because we work in perturbative regime, we can assume that these two functions are small, and we want to study the behavior as t goes to infinity. Okay, so the first step in understanding the dynamics is to try to understand the linearized equation. So for the linearized equation, a very important feature is that, so for the linearized equation, we can forget about the nonlinearity, and then you have this equation. A very important feature for the shear flow, which simplifies the analysis greatly, is that the equation decouples in the Fourier mode in X, right? Because you have the coefficients only depend on Y. So you can take Fourier transform in X because it's periodic in X, so you get the discrete Fourier modes for each. Sorry, this is omega you have infinite system of decoupled PDEs. You have partial omega k plus ik by omega k minus ik by psi k is equal to 0. And this psi k can be solved from omega k using this elliptic equation subject to the Dirichlet boundary condition. So this is the linearized equation, and we want to solve to understand the linearized problem as thoroughly as possible in preparation to understand the nonlinear problem. So the linearized problem has been analyzed by many people. Okay, this is actually an incomplete list. But so basically, assuming spectral stability, we can prove, roughly speaking, the following result. So this is exactly kind of like the example that we had. So your omega k ty can be written as fk ty times this oscillatory factor. Okay, so this can be seen if you forget about this mild non-local term. The non-local term is smoother than omega k, right? Psi k is smoother than omega k. So at least heuristically, let's firstly ignore this term. Then of course it will be exactly this, where fk is even independent of t. But if you turn on this non-local term, we can still write like this. This is still the correct way to write it. And then this fk will enjoy uniform regularity in y. So for example, one can prove bonds like this. So this would be, you know the omega k has this oscillatory factor given by this term, right? That's inevitable. If you want to get a smooth control over all times, you have to remove this oscillatory factor. After remove the oscillatory factor, you can hope to get some uniform in time smooth control. But here, actually, the control is not smooth. It's only H1. And all this can be seen if you ignore the non-local term in the equation. Okay, turning on the non-local term, the full equation is actually more complicated. So there are many works, as we have seen, but so maybe the most general result was firstly obtained by Wei, Zhang, and Zhao in 2015, who proved that proved exactly this. Okay, so you can prove this, and then from that you can get the decay of stream function and the decay of the velocity field, because if you look at this expression, then psi k is solved from omega k by integrating against the Green's function. But if you integrate against the Green's function, you have oscillatory factor integrating against Green's function. You can integrate by parts to get decay of psi k. So as long as you know you can decompose like this, then the decay of stream function can be obtained rather easily. Okay, so in fact, due to the boundary effect, the precise regularity of this fk, the so-called profile fk, is extremely complicated. And in general, we cannot expect uniform smooth control, not even H3 control. This is because the boundary terms, you have some boundary terms because of there's this boundary value. The boundary term will carry a different oscillatory factor. So the interior term will carry this factor, but the boundary term will carry a different oscillatory factor, and then these terms might interact and produce more complicated terms. So if we consider even the linear problem in a finite channel, to understand fk completely is actually a quite interesting little open problem. But if we assume further conditions to remove the boundary effect, basically, let's assume B double prime is compactly supported inside the domain, and also the vorticity does not touch the boundary. So these two conditions somehow kind of remove the boundary contributions. With these assumptions, then we can control fk in a Gevrey space. So basically, we modulo this. I think the key message is that modulo these boundary terms, you can prove the profile is Gevrey regular for all times, uniformly of all times. So this is a very important conclusion, because this is what is needed for the nonlinear problem. So for later reference, let us recall the so-called Gevrey space on t times r. If you have function f on t times r, let's define the Gevrey norm. So basically, you take the Fourier transform in both x and y. So because x is periodic, so you get the discrete mode in k, and then you have f tilde. You multiply this weight. Okay, so there's a parameter s. You multiply this weight and take the L2 norm. So in this norm, if s is equal to 1, then you have the analytic norm. If s, okay, so is between 0 and 1, you have this so-called Gevrey norm. So it's kind of, this space is kind of the interpolation between the Sobolev spaces and analytic spaces, but it has several interesting features. For example, you can find Gevrey regular functions which are compactly supported, and that's not possible for analytic functions. So this property gives us the crucial flexibility when we have to work with infinite many derivatives. So in a linear problem, if we do not have the boundary effect, then we can control the profile in Gevrey space. But then we want to extend that to nonlinear problem, and that's actually a challenging task, and was proved by Ionescu and myself in last year. And roughly speaking, we proved the following result. You assume that the background flow is monotonic, linearly stable, and linear near the boundary. Okay, away from the boundary. Then we can write the vorticity field. This is now the nonlinear problem. Okay, the omega k, the solution to the nonlinear Euler equation, the case mode of the vorticity field for of the 2D Euler equation. So omega k can be written as a profile times this oscillatory factor. Okay, so you see that here we have to be very careful about this oscillatory factor, because the oscillatory factor now depends both on the linear flow and on nonlinear correction. So because we want to control Fk in a very, very smooth norm, it's extremely important that you to capture exactly the right oscillation. Otherwise, if you kind of miss any oscillation because there's a t in front, that will result in a terrible loss, terrible growth in the Gevrey norm over time. But if we do this, then we can show that Fk is Gevrey2 regular in V uniformly over all times. And this is the most important conclusion in the in nonlinear implicit damping, because with this you can recover all the decay in stream function and velocity field, and one can prove that velocity field converges with rate at 1 over t. In fact, ux decays like 1 over t squared, uy decays like 1 over t. So that's kind of the nonlinear implicit damping result. But the key message is that you can control the profile, you can identify a profile with the correct, after the correct modeling of the correct oscillation factor, and get the profile in and control the profile in Gevrey space. So at the qualitative level, this uniform smoothness of profile together with the this monotonicity of B shows that actually the vorticity for the 2D Euler in the neighborhood of stable shear flow converges weakly but not strongly to a smooth final state. So this is a kind of actually one of the most attractive conclusion for me, because so you have you start with very smooth data, you perturb it with very smooth data, and then you converge it to very smooth data. But the process of convergence is extremely violent. You have weak but not a strong convergence. So this is a kind of violent relaxation process. And this is consistent with the 2D turbulence theory. So 2D turbulence theory predicts a transfer of energy to high frequency, but also a reverse transfer of energy to low frequency, because you have this emergence of coherent structures. And we have these spectral conditions, and the spectral conditions are satisfied by a very large class of background flows. So, okay, so Gevrey space, Gevrey regularity, that's, we have to assume that the perturbation is Gevrey regular, and this is likely sharp if we want to control the profile in as precisely as we did in the theorem. And actually, previously, there's a result by Lin and Zheng, who showed that if you allow rough perturbations in Sobolev spaces, in low regularity Sobolev spaces, then in fact you can find coherent structures, non-trivial coherent structures near the shear flow, near the coed flow actually. Lastly, let me briefly comment on the history of the problem. So for the first major result was in the nonlinear implicit damping for 2D Euler was obtained by Bedrossian and Mahmoudi for the coed flow on T times R. And also recently, just slightly after our work, there's a result by Mahmoudi and Zhao who proved a similar result. Okay, so that's the case for the shear flow. Now let's turn to the vortex problem. Okay, so for the vortex problem, so that's what we saw in the video. The vortex symmetrization problem, the general case, the full nonlinear vortex symmetrization problem is still open. Okay, we still cannot really prove that. I will explain why that's the case. So the only available results are for linearized flow, firstly done by Bedrossian-Coti Zelati-Vicol, and also recently by myself and Alex. I will explain what are the differences between these two works. And for the nonlinear flow, only near point vortex. Okay, so that's a special result for the nonlinear flow. So let me just very briefly go through the point vortex case. So point vortex is kind of a solution to the 2D Euler equation. So we perturb this point vortex by a smooth vorticity field, and moreover, we assume that the vorticity field is supported away from the point vortex. So the point vortex kind of is located outside of the cloud of the vorticity. And then you assume this is the solution to the Euler equation, and you plug in the Euler equation, you get this equation, where you have this extra velocity field. This is generated by the point vortex. So the point vortex will generate a rotation field. But this rotation, crucially, is not a rigid rotation. Okay, it's a differential rotation. So that the speed, the angular speed, depends on the radius. So this is the differential rotation that actually stabilize the whole situation. And moreover, the point vortex will be moved by the actual vorticity perturbation. So this is a kind of a coupled system between this point vortex, the position of the point vortex, and the perturbed vorticity field. Then we prove that if you assume that the perturbation is Gevrey 2 regular and the support is separated from the point vortex, then the point vortex will be always separated from the perturbation. Oops. And moreover, the point vortex will stabilize extremely fast to a final position, and then the perturbation will symmetrize around this final position to a radial function, and the radial function is smooth. So again, you have the interesting feature that you start with a very smooth setup, okay, smooth perturbation, and then you converge to a radial setup, and it's also the radial function is very smooth, but the convergence is extremely violent. Okay, so that's the point vortex case. Now, in the last 20 minutes or so, let me just turn to report a recent new result. So this is for the general vortex problem. Okay, so for the 2D Euler. So here we consider a vortex, which is vortex is a radial vorticity field for 2D Euler, and it's automatically a steady state. So here we assume that the vorticity, so the radial function is decreasing, radially decreasing, strictly decreasing. Okay. Then, so this radial vorticity will generate this differential rotation. So just like the point vortex case. So in this case, it's most convenient to work with polar coordinates. So in the polar coordinates, you have this velocity field, UR E theta, and the vorticity field is given by omega r, which is a radial function. Then from the Beer-Savart law, this UR satisfies this equation for which connects the velocity field and the vorticity field. And then we can write down the linearized 2D Euler equation again. The 2D, so okay, so the 2D, so here we already linearized it, so there is no nonlinear term. You have partial omega plus UR r partial theta omega minus this quantity partial theta psi equal to 0, and psi is solved from omega using this Laplace equation in R2. Okay, so this is almost like before, right? This is almost look like the shear flow case. You have this term partial theta. Previously it's partial x, but now it's partial theta. Of course, this equation is a little more complicated, but I mean, at least structurally, it looks like the shear flow case. Again, for the vortex, an important feature is that we can take Fourier transform in theta and decouple the equation into Fourier modes. So take Fourier transform in theta. Of course, theta is periodic, so we have this discrete Fourier modes. Your k is in z, t is positive, and r is from 0 to infinity. So r is the radius. We have partial omega k plus ik ur over r omega k minus ik omega prime over r psi k is equal to 0. Again, ur is a velocity field. Ur e theta is a velocity field, and omega r is background vorticity field. We assume that omega r is decreasing, so omega prime is less than equal to, strictly less than equal to 0, unless r equal to 0. So because it's similarity to the shear flow, one might expect that we can, just like in the shear flow case, define a profile, because you have this guy which generates this oscillation. So let's remove this oscillation and then get this profile, right? It seems that it's reasonable to define profile like this. Omega k cannot be uniformly smooth in R, but maybe after removing this oscillatory factor, you get this profile. Maybe one can prove that this guy is uniformly smooth in R over all times. So actually, this was attempted by Bedrossian-Coti Zelati and Vicol, and they actually proved a sharp result in this respect. They proved that you could actually control Fk in some Sobolev spaces. So you take a few derivatives in R. The number of derivatives you can control depend on K. Okay, so we will explain why that's the case. So you can control a few derivatives in K in R, but not all. It seems that it's hard to control all derivatives in R. Actually, we in the work with Alex, we found that in fact this is impossible. So you cannot control Fk in a smooth norm in R for all times. And this is due to the degeneracy of UR over R. So if we assume omega R is a natural object, like a smooth function, smooth fast decaying function, then automatically this condition is satisfied. Partial R UR over R at R equal to 0 is equal to 0. So this is the degenerate function. So UR over R, so the oscillation is not uniform over all R. When R is equal to, okay, when R equal to goes to infinity, it's also degenerate, but actually that situation turned out to be much simpler. So the main issue is when R equal to 0, this guy is degenerate. So in fact, instead we should decompose using two profiles. So we should write omega k as the first profile time which carries this oscillation factor plus a second profile which does not carry this oscillatory factor. This second profile is mostly associated with the R equal to 0. So basically it's like it's given by the non-local contribution due to the origin of the plane. Now we can show that this guy is uniformly smooth in R for all times, and this guy is uniformly smooth in R for all times. And actually we can show they are Gevrey smooth in R for all time if your initial data is Gevrey smooth in R. So then we can see that why we cannot really define one profile like this, because this guy is already smooth, right? This guy is already smooth. Now, if you multiply the whole vorticity field by this oscillatory factor, that's good news for the first profile because you cancel the oscillatory factor, but not so good for the second profile because then this guy is already smooth. You multiply this guy, you kind of artificially introduce this oscillation. The reason why, even with the kind of almost like a wrong profile, Bedrossian-Coti Zelati-Vicol can still obtain this amazing control in some Sobolev space, is that this Fk2 actually decays over time. The rate it decays depends on K. So for larger K, actually depends in time with a faster rate. So okay, so that's why. So you have this function. Which is already smooth, you multiply a kind of oscillatory factor anyways, but you can still control it in some Sobolev space because this guy decays, right? So then it balances the growth of derivative of this factor. But you can only manage it for so many Ks because the decay is not unlimited. The decay of this guy is not unlimited, it's limited. So that's why you can only obtain, if you define a profile like this, you can only obtain Sobolev control on the profile for finitely many derivatives depending on K. Okay, so that's kind of the high level result, that high level, very high level what we proved. But let me just go into some of the details. Oops, sorry, I think oops. So let me go into some details here. So you have, so we have this UR, which is a UR E theta gives a velocity field. So UR divided by R, let's denote it as BR. And the omega prime, omega R is the vorticity field. Omega prime R over R, let's denote by DR. Then from the equation satisfied by the linearized flow and general spectral representation theory, we can have the following formula. So we can actually represent psi k, the stream function, the case mode for the stream function, as this oscillatory integral. Okay, as this oscillatory integral, where this functions psi, this is what we call the spectral density functions. So they depend on both on the physical space variable R and the spectral parameter R naught. Okay, so it has these two parameters. So it encodes both the spectral information and the physical space information. So these objects really give everything about the linearized flow. So if you know these guys well, then you know everything about the linearized flow. And moreover, these objects, the so-called spectral density function in the variable R and R naught, satisfy this this equation. Okay, so you have dr divided by this. So the main issue, so in the end, everything is reduced to analyzing these functions. For example, if we want to obtain quadratic in time decay over for the stream function, in this formula we just have to integration by parts twice, right? Because every time you integrate by parts, you get a 1 over t. So we just have to understand, for example, the regularity of this guy in R naught. So we have to take two derivatives in R naught. If we can take two derivatives in R naught, then we can get 1 over t squared decay. Now, the main issue with analyzing this equation is that the equation contains a very serious singularity. You have the singularity is 1 over R minus R naught when R is close to R naught. So this singularity is main kind of difficulty in understanding the regularity property of this guy. And also there's another source of kind of confusion historically. That's you see that we have to integrate by parts in R naught in this formula, where R naught is the spectral parameter. But this equation is in R, right? We have to understand this the regularity in R naught, but somehow the equation is written in R, not in R naught. So that's another kind of a point of confusion here historically. Oops. So it turned out for our problem, it is more convenient to work with, instead of with the R variable, it is more convenient to work with the V variable. So V is log R. So R is equal to E to V. So in this way, we can ignore the fact that R is in a boundary, has some boundary. So R has, in this problem, R starts from 0 to infinity, so there's a boundary. But if we switch to V, then V will be on the real line. So that's kind of a convenient. We don't know. At this moment, I don't know how essential it is to work with V, but there are some positive signs of working with V, because we can get very nice singularity structure for the spectral density function, as we will see in a little bit. Okay, so now let's switch everything to the variable V. Okay, so V is log R. Now V is on the real line. So we can write this spectral density function in a V W variable. Okay, W is log R naught. Okay, R naught is E to V. Now V and W are both in the real line, on the real line. Moreover, we can write BR as capital BV, DR as capital DV. Again, everything is switched to the V and W variable. And moreover, we also write the initial data as in the V variable and the stream function in the V variable. So now we want to work with the V variable. So it's some calculation, but it's a straightforward calculation to switch everything from R naught variable to VW variable. So already we gain some clarity by working with the V variable, because the main equation for the spectral density function is simplified. I mean, it looks like it's simplified, right? The main term at least is constant coefficient now. You have k squared minus partial V squared. Instead of this R minus 1 partial R or R minus 2, now you have this constant coefficient equation with this non-local singular and singular potential term. Okay, so there's a singular potential term. You cannot really remove the singularity at this point. The singularity is still there. 1V is equal to W. So for example, we would expect this spectral density function to have a singularity when V is equal to W. This is not surprising because this spectral density function corresponds to continuous spectrum. You collapse the spectral parameter into the continuous spectrum, and when you are close to spectrum parameter to the spectrum, of course you expect some sort of singularity, and the singularity is reflected in this problem as a singularity between when V is equal to W. And also we can write down the formula connecting the spectral density function with our stream function in a new variable. So now everything is really reduced to understanding the spectral density function pi. Okay, so we want to understand these functions. So actually it's maybe good to get some idea of how these functions like. So this B, so B decays like E2 minus 2V, but a very important feature is that B prime is degenerate both at V is equal to as V goes to positive infinity and negative infinity. So B prime is degenerate in both directions. And moreover, B prime V has this asymptotic expansion when V goes to minus infinity, and dV also has this. dV actually is equal to almost equal to constant when V goes to minus infinity. It also has this asymptotic expansion. These properties are important to determine the size of the potential. It turns out that the potential is not completely negligible. In fact, it plays a major role when W is negative. The main thing is that, so usually it has a singularity, right? It has singularity, so that's in that way it will affect the regularity structure of this guys, the pi. But the singularity is not very strong. The singularity is manageable. It's a principal value type singularity, so it's still dominated by this term. A more serious issue is when W is negative and very large negative. This guy is not small. Okay, it's not decaying. It's actually equal to a constant for a very long interval. So that makes it impossible to be dominated by this guy, because this is equal to 8, actually approximately equal to 8. If we use this formula to calculate, we can see that this is approximately equal to 8 on the interval from W to 0, if W is very negative. So then you have this. So then this is a highly non-local potential. Then to analyze that, we have to do something. We cannot really view this as the main term. We have to remove part of this potential and put it into this term and treat that as the main term. So that's why this kind of expansion are important. That's also why this degeneracy changes the behavior of the problem from the shear flow case. For the shear flow case, this potential is not very, except that it contributes to a singularity. Other than that, it's not very harmful. Okay, so the main conclusion is a little technical, so bear with me for a second. So I have to introduce a few notations. So okay, so if we look at this equation, sorry. If we look at this equation, you see that okay, when k is very, very large, this equation will give you a very fast decay as v goes to infinity, because you have k squared minus partial v squared. This equation is solved on the real line, so we expect the function to decay like exponential to minus k. Okay, exponential to minus kv. So that's the kind of the rate of decay we would expect, physical space decay we would expect. So that's an extremely fast decay. But on the other hand, this k is also, it's not a kind of an independent variable. It's also a derivative. It's a derivative in the theta variable. So this creates a kind of a little bit of confusion, because it's not only a derivative, but also indicates the physical space decay. So we want to somehow decouple the two. Therefore, we choose not to track all the decay for large k, physical space decay. Rather, we introduce this cutoff function, cutoff frequency. So we will introduce this k dagger from 5 to infinity. So let's just fix it. And so although we know that our function might decay like exponential to minus kv, we will not capture this information. Rather, we will only capture the exponential decay for the first few modes, and for higher modes, we will stop capturing the sharp decay, because then it would not be possible to simultaneously also capture the best regularity. And for us, we believe that the regularity is more important than the physical space decay. So let's fix this k dagger and introduce this parameter. So for small k, this guy will be just equal to k. But for k bigger than k dagger, we will just treat it as k dagger. And in the end, the decay we will get for large k is just the E2 minus k dagger v. Okay, so that's our choice. We can choose k dagger large, but we want to fix it for large k. And also this mu k. This mu k is very important. It captures this enhanced decay due to the potential. Actually, the potential will do something good for us, in fact. So the potential term will contribute 8, like the number 8, on a very long interval. But 8 is positive, right? You have k squared plus 8. So that's part of that's the man term. Instead of k squared minus partial v squared, the man term would be k squared plus 8 minus partial v squared on a very long interval. So that's why you have this number. This is related to the so-called vorticity depletion phenomenon. And there's another number. This number is not very important. It's just chosen to be bigger than mu k, and then we choose this cutoff function. So we have to assume, we make some assumptions on initial data. Again, this is also a little, I apologize for this. This is also a little technical. So basically, what do we assume? So because you see that the situation is a little complicated. We have both. We need to capture both Gevrey regularity of the function, but also physical space decay. So the coupling of the two makes both the assumptions and the conclusions a little complicated. But in the end, everything is actually quite optimal. So this is my initial data. So for smooth data, I would expect the E2 minus kV, E2 kV kind of decay as V goes to minus infinity. So that's the natural rate. So I want to extract this decay. So I want to extract this man term, remove this man term. I have this F naught k. So the main purpose is to see that this guy actually now decays a little faster as V goes to minus infinity, because I have extracted the man term. Now the assumptions are, instead of on little fk, the assumptions are imposed on capital Fk. Capital Fk are assumed to satisfy the following conditions. So you localize at the place J. I mean, that's where this is a little technical, because we have to capture both physical space decay and regularity. But if we localize around the location J, then we assume this is Gevrey regular with this precise weight. Okay, you multiply this weight, and then you take L2 norm. So this is exactly Gevrey regular. So the main point of the weight, the choice of the weight, is also dictated by nonlinear application, because in a nonlinear problem, this is exactly the weight we use to measure the regularity. That's why because we want to apply to nonlinear problem, so we insist on very precise weight here. So you see that, okay, so this Gevrey regular, and also it's bounded by this factor, which encodes the physical space decay. So basically, it says that as J goes to minus infinity, it decays like E2 mu var kappa k star J, and as k goes to infinity, as J goes to positive infinity, it decays like E2 minus k var kappa k plus 8. So it has relatively fast decay at infinity, has the natural decay as V goes to minus infinity. Okay, so then with this condition, what can we prove? So my objective is to control the spectral density function. So the spectral density function is defined as the imaginary part of these objects. So we can show that they exist as epsilon goes to 0, the limit exists. This function is well defined. And then our main conclusion is about the regularity of this guy, the regularity and decay of this guy. So as we have indicated earlier, this function is not completely smooth. Actually, when V is equal to W, it's singular. So it's singular when V is equal to W. So in order to capture that kind of very precise structure of the singularity, we make the following changing variable. So instead of looking at the VW, we shift the variable to V plus W and W. In fact, now if we make this shift, it turned out that this changing variable will shift all the singularity to W, and that all the singularity to V, and W is now smooth. So that's our kind of main conclusion. Well, after this shift, this function will be Gevrey regular in W as in the same Gevrey space as the initial data, and it is not regular in V, but we have very good singularity structure in V. So okay, so this is a more precise statement. I think I have like maybe 2 minutes. So again, the statements are a little complicated because we have to capture the precise regularity and the physical space decay. So every time we measure the regularity, we have to first localize into a position, localize to a position, and then take a Fourier transform, and then measure its regularity in Gevrey space. That's why it's a little complicated. But basically, here the key point I want to emphasize is that this exactly, so you localize into an appropriate place when V is away from 0, or you localize to appropriate place, then you can measure regularity in W. So you take Fourier transform, W becomes eta, V becomes psi. Then this is it's Gevrey regular both in V and W because V is away from 0. So if V is away from 0, then this function is smooth in both V and W. So you can actually, moreover, it's more smooth in V than the data. Okay, it's more smooth in V than the data. And also you have the decay. But if V is close to 0, then this function is no longer smooth in V. It's smooth in W, but no longer smooth in V. And we have very precise norm to control it. In fact, you can take 2 derivatives in V. It will be like a Dirac mass. So this function has only 2 derivatives in V before it becomes a Dirac mass. But it's as smooth in W as the initial data, moreover coupled with the right physical space decay. And CDK also satisfy a very nice equation. But okay, so now we have seen that CDK is not smooth in V. Okay, so it's smooth in W, but not smooth in V if V is near 0. But remarkably, it has a structure. We have a very precise structure on the singularity. So it's not smooth in V. But if you take a smooth function zeta, and then you make this change variable, you take zeta V plus rho minus zeta rho. This is okay. So you cannot use say composition of smooth functions to determine the smoothness in rho, right? Because you know this variable is not smooth. But remarkably, this function is actually smooth in rho. So that captures also the structure of singularity in the first variable when the first variable is close to 0. So all this allow. So we also have this very nice formula connecting theta k and phi k. So all this will allow us to define these profiles by localizing away from when V is away from W or V is close to W. The first, when V is close to W, you get the profile which you have to normalize by introducing this oscillatory factor. But for V away from W, we do not have to normalize. It's automatically already smooth. And why we cannot get faster decay? Well, this is a smooth in V, that's not a problem, but its decay in W is limited. But this guy is degenerating in W. So if you take derivative in W, B prime W is like e to minus absolute value of W. So every time you integration by parts, you have to eat up some physical space decay, which is exponential. So you can only take integration by parts several times before you eat up all the decay, and then you stop. So that's why this guy is very smooth in V, but it has limited decay in T, which depends on K. Okay, so I had some, but okay, I think I should stop here without going through the detail of the proof. Thank you. So sorry for going over time.
Thank you, Hal. Anyone have any questions? Let me ask, so in the first part of your talk, when you talked about the case of the strip, basically the periodic strip, you talked about your result, which involves Gevrey regularity, but then you also mentioned a result that involves only Sobolev and and you said that they're basically your sort of symmetrization type result doesn't hold. Did I understand it right?
Yeah. Okay. So maybe that's the result that's the result for Lin and Zheng, right?
Yes. Yes, I think so.
So okay. So they perturb. I believe they perturb solutions in a pretty low Sobolev space like H2. Okay, less than H2. So the problem with perturb this is that you actually change you already change the linearized operator sufficiently. You have kind of introduced the sufficient change to a linearized operator, such that to the extent that you actually created the unstable eigenvalue, almost to that extent. So because everything's very delicate, right? If you perturb it in a rough space, you might change already the background sufficiently so that you actually introduce some instability to the problem already. So I think what is a more interesting, even more interesting issue is to understand in sufficiently high Sobolev space, but not infinite the smooth category, what happens, right? I think that would be a wonderful, but it's a very hard problem. I think
it was actually
behavior could happen. Yeah,
that was actually exactly my question. That do you have a feeling for where is the borderline, and at which point do you start seeing the nice symmetrizing behavior?
I have no idea. I don't know if it exists actually. It seems that if as long as you leave Gevrey 2, all sorts of things can happen. That's my feeling. So all sorts of things can happen. You might have a really complicated dynamic. But on the other hand, if you have viscosity, then everything is automatically Gevrey, right? So there's no finite regularity space, because if you have Laplacian, then everything is Hit equation. So like Hit equation, so everything is Gevrey.
Any other questions? I want to ask one more.
Okay.
So that's about the second part of your talk. So you assume that the vorticity is radially monotone, right?
Yeah, radially decreasing. Yes.
Decreasing. So that means it's 0 at infinity, and then it becomes negative and decreases, right?
Right. So vorticity is like a Gaussian. It's like a Gaussian function.
So sorry. I mean, becomes positive. Yes.
Right.
I mean, it doesn't matter because it just changes sign, changes direction of rotation. So yes, but so I mean, clearly this is a crucial assumption for you. But I guess the question is how serious, would it be to remove that assumption? I mean, is it like completely going to blow up the whole analysis?
Well, if you do not assume strict monoticity, I think on the spectral level, you could have some problem. You could generate some unstable eigenvalue, which correspond to some structures. So I think that's understood in the physics literature, where they have some, say, racking vortices or some other issues. I haven't really. But my belief is that if you do not assume that assumption, the linearized operator has some issues. You could have eigenvalues.
I see.
Yeah. Also the behavior for BR. So BR, it's very important for us that BR is also monotone. If omega prime is not negative, strictly negative or strictly positive, then this BR might not be monotone, and then there could be other issues. So yeah, the baseline is that we want to handle the easiest case, and the easiest case in this case is a little not so easy. So
right. Yeah. I was asking because in a sense, this is maybe not a physical situation, but if you could actually change sign of the vorticity, right, you could get to a point where essentially you have this funny vortex that in the center it doesn't rotate and there is no vorticity, right? And then you could basically just sort of have an annulus type of vortex, and then maybe you could just apply the approach you had from the strip, right? And show that the vorticity never reaches the center.
Oh yeah,
right?
Okay, so I think that's a very interesting discussion, but you see that I think, okay, I showed you this video, but I don't want you to believe that's the only scenario that could happen, because the physicists also explored other possible final dynamics, not final dynamics, but like coherent structure which exists for extremely long time, where they found this triple vortices. So instead of have one center which axisymmetrizes everything, you could have three centers, which form like a kind of a very concentrated vorticity region. But you have three centers exactly with different signs, and then they rotate together for a very long time without merging, without symmetrization. So I think that happens when you perturb things so big that the background flow becomes non-monotonic, and then strange behavior could happen. So it's a relatively complicated scenario in that case.
Mm-hmm.
Yeah.
Yeah. Okay. All right. Any other questions?
So I wonder, what if the vorticity at the center is infinity, but it's still monotonic?
I
something
think
like the inverse power singularity.
That's a very good point. I think it could potentially simplify the analysis.
That's what I
guess.
Right?
Because it kind of make it less degenerate.
Yeah.
The issue is
degeneracy at the center.
Yeah. I think that could potentially stabilize things a little further.
Okay.
But here it's very bad because this guy is B prime at R not equal to 0 is equal to 0. So that's very bad. But if you allow some singularity so that B prime maybe not vanish, right? It's like maybe constant. If it's constant, then it's already very good.
Yeah, but of course, then you have a problem with even well-posedness, right?
Yeah, possibly. So yeah,
this is
you have to have some trade-off. Yeah.
This is sort of replacing the case with the point vortex, right? But in that case, at least you have well-posedness, whereas in this case, you don't really, right? So
well, you could imagine a singularity where you have this power law, but with really weak power law.
Yeah. Okay. Yes, that's true.
Right? Okay, I don't know. Like you have to play the game really delicately. So
yeah.
But this is already quite challenging because this guy, the man message, I wanted to convey this message, but somehow my apology that it's a little more technical. So the potential is not completely negligible. I think that's the main thing. So this guy actually is equal to, okay, maybe I should point here. So this potential is equal to 8 on a very long interval. So you have to incorporate that into the man part to really treat what is left as a perturbation.
And do you happen to know in these simulations that Theo did, the vortices that, after some time when you only get like a couple of those vortices, do they look like the vorticity is monotone radially?
I think in the physics literature, they always assume it's a monotone. So it's okay. So here it's just I think Theo probably has the raw data. I don't have the raw data. Probably he has the raw data where you can read off. So we can play the video for a long time. Unfortunately, there's no button. I cannot speed it up. So it could run for a long time. In the end, you only have 2. And it looks like it's monotone because you have this color, right? In the center, it's more deep. The red is deeper.
Yes, it does look like that, but there is no. I mean, there may be a physical reason, but I don't think there is any mathematical reason why it should be like that. So, if you could just set up your vortex to not be like that, and then it may just if it's radial, then it survives forever like that, right? So. So it would be interesting to see whether there is sort of like numerically you do get that, but
I see. Okay, yeah. So I think it would be interesting to see if you have non-monotone. Can you find like non-monotonic
vorticity distribution, right? Radial vorticity distribution, which is somehow still stable, right?
Yeah.
I think for the recent work of Choi, Kai Choi, you know him, right? He was in medicine.
Mm-hmm.
He proved the nonlinear stability of this by using the Arnold's method, like Arnold-Casimir method. He assumed this is radially decreasing. So I think it'll be a wonderful result if you can show for some non-monotonic vortex, you can still have this nonlinear stability, because that would kind of really genuinely broaden our perspective, right? Yeah. What happens in that situation? You have non-monotonic, and then it's still stable. But that probably you cannot prove nonlinear stability using Arnold's method. Maybe you have to use some other method. So.
Okay, any more questions? Yeah, this is a very lively discussion, but I guess it's time to end it then. So thanks a lot, Hao. It was very nice.
Thank you very much for being here. Hope to see you on some occasion.